In this video, I'll be discussing the worksheet Stoich Wars, a New Stoich. So what this worksheet is a basic introduction to the process of stoichiometry where we do full stoichiometry problems. The last worksheet we were just working with mole conversions and using the mole ratio. This one combines everything that we know from the last unit with that mole ratio that we just learned, and it creates some pretty long conversion problems. What we have here for you is a map that shows you the path for conversions in these different problems. And as it explains up at the top, stoichiometry is the process of going from talking about the quantity of one substance in a chemical reaction to talking about the quantity of another substance in a chemical reaction. So what really changes this from the last unit is that we're talking about two different substances within one chemical reaction. In the last unit, we limited ourselves to talking about one substance. All right, in this one, we'll be using the mole ratio to go between different substances. All of the problems on this sheet fall in the line of this, what's called a gram-to-gram problem or a mass-to-mass problem, where we start here with the mass of one substance, and we're trying to get to the mass of a different substance by the end. So what we have to do is we have to convert from mass of the first substance to moles of that substance, and then we go from moles of that first substance using the mole ratio from the balanced chemical equation, all right, and then we go to moles of whatever our second substance we're interested in, and then we have to go from moles of that substance back to mass. And so there are actually three conversion factors here. There's the molar mass of the first substance, there's the mole ratio, which comes from the balanced chemical equation, and there's the molar mass, which comes from the periodic table again. So I'm going to give you an example here of one of these problems. It says a businessman has access to a large supply of KClO3. His desire is to produce, bottle, and then sell oxygen gas. In this process, KCl is produced as a byproduct. What mass of potassium chlorate is used if 2,500 kilograms of oxygen are produced? So there are a few things going on in this problem. Again, first of all, we're going through this process, the mass of a substance to moles, and then to moles of the second substance, and then to mass of the second substance. And so what we need is we need three conversion factors. We need molar mass for the first substance, we need molar mass for the second substance, and we need the mole ratio, which comes from the balanced chemical equation. So what we're going to do is we're going to balance this chemical equation, which isn't too bad. It looks like this. All right, and then we have to find the molar mass of the two substances that we care about. The two substances are oxygen, which is O2. From the periodic table, that molar mass is 32.00 grams. All right, the other one we care about is KClO3. Molar mass there is 122.55 grams. Okay, so then we start with the number that's given in the problem. Now this throws one little extra challenge in there. It gives us the mass as 2,500 kilograms. Typically speaking, we would want that in grams, and so we're going to convert 2,500 kilograms to grams. So that is 2,500,000 grams. Right. We would do that through the King Henry died by drinking chocolate milk metric conversion that we learned earlier on in the year. And so that's our starting point. Is we start with 2,500,000 grams of O2. All right. We want to get eventually to grams of KClO3, but to get there, we need to go through a few different things. So we go from grams of O2, if you remember up above, O2 here is our substance number 1. So we're going to go from grams or mass of O2 to moles of O2. All right, that's this first step here. We're going from grams of O2 to moles of O2. And so we have to think, okay, how many grams of O2 are in 1 mole of O2? The conversion factor as listed there is the molar mass, which comes from the periodic table. So we know the molar mass, we've calculated it already, it's 32.00 grams in 1 mole of oxygen. That's the molar mass. Okay, the next thing we need to do is we need to go from talking about moles of oxygen to talking about moles of KClO3, because KClO3 is our substance B. All right, so we're going to go from moles of one substance to moles of another substance. To do that, we're going to use the mole ratio that we learned from the last set of problems. And so for this one then, we have to look at the balanced chemical equation. We're going from moles of O2 to moles of KClO3. And so you just look at what numbers in front of them in the balanced chemical equation. There's a 3 in front of O2 in the balanced chemical equation. There's a 2 in front of KClO3. So that's 2 moles of KClO3 for every 3 moles of oxygen that are produced. All right, and then as a last step here, we need to go from moles of KClO3 to mass of KClO3. All right, so we're going to use that second molar mass again. We want to go from moles of KClO3 to grams of KClO3. In 1 mole, there's 122.55 grams. We had calculated earlier. That comes from the molar mass on the periodic table. So then we have to think sig figs. The mole ratio is infinitely many sig figs. When we give the molar mass, it's grams per 1 mole, and that 1 mole is infinitely many. So really we have a limitation here on that first number we were given is really just 2 sig figs. So we end up with just 2 sig figs in our answer. And what we end up with here is 6,400,000. If you round to 2 sig figs. And that is grams of KClO3. Okay, I'm going to speed things up a little bit on this next one. So same process. We're going to go here. It says ammonia, NH3, is a helpful cleaning solution and can be produced by combining nitrogen gas and hydrogen gas. Nitrogen is abundant in the atmosphere and is not dangerous, while hydrogen is explosive and must be gathered from water. A business opportunity exists, but working with hydrogen gas is dangerous. How many grams of hydrogen are necessary to react completely with 99.89 grams of nitrogen in the below reaction? And so on this one, we're going from grams of nitrogen to grams of hydrogen. All right, so the 2 substances we care about are nitrogen and hydrogen. We got to get our conversion factors. So one of them comes from balancing the chemical equation, which I'll do now. You need a 3 here in front of the H2 and a 2 in front of NH3, and then that's balanced. And the other thing that we need to do is we need to take N2 and find its molar mass from the periodic table. That's 14.01 times 2, which is 28.02. All right, for the H2, that's 2 hydrogens, 1.01 times 2, so we end up getting 2.02 grams. So get your 2 molar masses that you're going to need from the periodic table, and then we're going to start the conversion here. We start with the number that's given, 99.89 grams of N2. All right, and then we're going to try and get out of grams of N2, so we put it down on the bottom. And we want to get into moles of N2. All right, and so then we want to cancel out moles of N2, so we put moles of N2 on the bottom. And we want to get into moles of H2, because that's the substance we're interested in. Then we cancel out moles of H2. And we want to get into grams of H2 because it asked us in the end for mass of hydrogen, or how many grams of hydrogen. All right, then we just need to write in the conversion factors here. First one, grams to moles for N2, you're using the molar mass. That's that 28.01 grams in 1 mole. All right, then we use the mole ratio. H2 has a 3 in front of it, so 3 moles H2. N2 has a 1 in front of it with a coefficient in the balanced chemical equation. All right. And then grams to moles for H2. we got 2.02 grams in 1 mole. It looks like we have 3 significant figures in this problem because 2.02 limits us to 3 sig figs. And so when you do that, you should get 21.6 grams of H2. Okay, so for problem number 1 here, it says you determine that last reaction that we were doing is safe, and then ammonia production can begin. How many grams of ammonia are produced in the reaction from practice number 2? Okay, so in this one again, it's the same equation, so we just write it in. It's balanced here. There's a 3, and then we've got a 2 on the other side. All right, important molar masses here. We're going to start again with N2, so I'm going to write its molar mass again is 28.01, all right, grams. And then we also need the molar mass of NH3 for this problem. All right, NH3 has a molar mass of 17.04. From the periodic table, we just take the mass of nitrogen plus 3 times the mass of hydrogen. Okay, now we have all the conversion factors that we need. So we're going to start with the same number because it says it's the same situation from practice problem number 2. So we start again with 99.89 grams of N2. All right, and then our hope is to cancel out grams of N2 and get it into moles of N2. And then after that, we want to cancel out moles of N2 because we go from moles of N2 to the moles of the other substance we want. In this case, we're trying to get it into moles of NH3. All right, then once we're done with that step, we have to get from moles of NH3 to grams of NH3 because it asks us to determine how many grams of ammonia are produced. So writing in the numbers here, mole to mole ratio, first one, gram to mole, that's the molar mass. So we take 28.01 grams of nitrogen in 1 mole. Then we do the mole ratio. You look at the coefficients on the balanced chemical equation. In that chemical equation, NH3 has a 2 in front of it, N2 has a 1 in front of it. All right, so we've got 1 and 2 there. And then going from moles to grams for NH3, moles to grams is the molar mass again. So we know 1 mole is 17.04 grams. On this one, we're going to end up having 4 sig figs because all the numbers have either 4 sig figs or they're those perfect numbers, which have infinitely many. And so we end up with 121.5 grams of NH3. All right, number 2 here for your practice problems. It says silver chloride can be used in many industrial processes and can be extracted easily from silver nitrate. How many grams of silver chloride are produced from 6.200 grams of silver nitrate according to silver nitrate reacting with barium chloride? So in this one, we're starting with 6.200 grams of silver nitrate, that's AgNO3, and it's asking us about silver chloride, that's AgCl. So the first thing I'm going to do is balance this chemical equation. We need a 2 here, and a 2 here, and then everything else works out. The other thing is we need to find the molar masses for those 2 substances that we're interested in. So AgNO3, if you find those masses on the periodic table and add them up, you get 169.88. For AgCl, if you find those on the periodic table and add them up, you should get 143.32. All right, so we start off here. Start with the mass that's given, 6.200 grams of silver nitrate. That's AgNO3. All right. That number, by the way, has 4 sig figs because those are trailing zeros, but there is a decimal point, so that one is 4 sig figs. Then we're going to get out of grams of AgNO3, and we want to get into moles of AgNO3. Okay, then we get out of moles of AgNO3. And into grams of AgCl. Oops, sorry, moles of AgCl. Jumping ahead of myself. Then we'll cancel out moles of AgCl for grams of AgCl. Conversion factors, starting here on the left, going from grams of AgNO3 to moles. That is the molar mass. So we take the 169.88 grams in 1 mole. All right, for the next step, going from moles of one thing to moles of another thing, we're looking at the balanced chemical reaction and finding the coefficients. There's a 2 in front of AgCl up in the balanced chemical equation. There's also a 2 as a coefficient for AgNO3. All right, so it is a 2 to 2 ratio. And the next thing we need to do is we need to get to grams of AgCl by using its molar mass. So it's 1 mole of AgCl is 143.32 grams. In this one, we end up having 4 significant figures because 6.200 has 4 significant figures, and that limits us to 4. If you multiply that out, you should get 5.231 grams of AgCl. Okay. I will not do the last problem, but you can find the solution to that online in addition to an entire other practice set of these problems. And so the idea with these, they're all pretty much the same process. They're going from grams of one substance to talking about grams of another substance. We'll do more practice problems later where you're doing some other conversions within this flow chart that we've shown you here at the top of the first page, because you can go from any box on here to any other box. All right, but I wanted you to see a normal type of conversion so that you could get an idea of how this works. But you can go from, say, talking about particles of one substance to talking about volume of another substance and things like that. And so really trying to get how all of these things fit together and knowing your conversion factors will really help, because eventually you need this entire flow chart sort of dedicated to memory in your head so that you know where to go from anywhere else inside one of these sets of problems.